Today we're going to start our last chapter in chemistry, which is about nuclear chemistry. So these reactions that we're going to talk about are very different from the other 5 types of reactions that we did earlier in the year because this time we're not dealing with electrons. We're going to focus on the nucleus in the center of the atom. And if you remember from way back a long time ago, the nucleus has 2 particles in it, the protons and the neutrons. And when we change the numbers of those, they're called nuclear reactions. These are independent of other energy influences. And the reason that we even have these, or the reason that some elements are radioactive, you've heard that word before, has to do with how many protons they have in the nucleus. So if you remember that protons are positive, they repel each other. They don't like each other. So if you have too many protons in the nucleus and not enough neutrons to buffer that repulsion, they will spit out particles and they'll give off things, and that's what radioactive decay is. So just like most of our topics in chemistry that we've talked about, when you are asked, why does something happen? And almost always the answer will be to become stable. And that's the same thing with this chapter. So during a nuclear reaction, the law of conservation of mass has to be conserved. Same thing as before, that we have to conserve the number of, or the mass of the reactants and the mass of the products. So what I wanted to review first is this little symbol here. It's called an isotope symbol. The top number is the mass number, and remember that includes the protons and neutrons. The bottom number is the atomic number, which is just the protons. So as we do some of these reactants, the main thing is we need to keep the amounts of protons and neutrons the same on each side of the arrow. There are 3 different particles that we're going to talk about, and the first one is an alpha, and you do need to memorize this symbol. So go ahead and get it into your head. This is why I'm doing it towards the end of the semester, so you'll have it fresh in your brain for the exam. An alpha particle is called, it's basically just a helium nucleus, and it has a mass of 4 with 2 protons. It's basically just a helium atom. This is the biggest of the particles that we're going to talk about, which means it has the lowest energy. So these are not very dangerous because they're so heavy and they're so big they can't even go through your skin. They can be stopped by a sheet of paper or by your skin. And it has a charge of +2. So when we're doing these decay problems, if you ask me in class, I can show you a little bit easier. It's going to be hard to show you on here, but basically what you're doing is you're starting with these top and bottom numbers, and 238 is the total and 92 is the total. So on this side of the arrow, first of all, if it says alpha decay, and it will tell you that in the problem, it has to tell you what kind of decay it's going to be. So if it says alpha decay, on this side of the arrow, what I want you to write is helium with a 4 at the top and a 2 on the bottom. Because if it's alpha decay, it means it's giving off a helium particle. Then you're going to write plus, and then you just need to do some basic math. So if our total mass on the left is 238, our total mass on the right also has to be 238, but we just took out 4 particles from the alpha particle, so 4 is on the top over here. So if you do 238 minus 4, you get 234. So for our other particle on this side, we've got a 234 on the top. Do the same thing with the bottom. So our total needs to be 92. That's what's over here on the left. The alpha particle has a 2 on the bottom, so the other particle will have a 90 because 90 plus 2 will give us the 92 here. So again, we've got a helium particle with a 4 and 2, and then over here we've got 234 on the top with a 90 on the bottom. However, if you remember way back a long time ago that the number of protons determines the type of atom. So now that we have, or the type of element, now that we have changed the protons in this element, 90 is different from 92, you're going to get a different element. And so you just have to go to the periodic table, find the element that has 90, which happens to be this one right here. So this is what you should have in addition to an alpha particle over here on the side of the arrow. Then you can do it 2 more times. So go ahead and write your helium 42. Go ahead and do your addition and see if you can figure out which elements they are. And then this last one is just a little bit different. If they give you a dash with a number here, that is the mass number. They don't have to give you the protons because you can go to the periodic table and find radon. It's in the bottom right corner. It has 86 protons, and that's what makes it radon. So you don't have to try to figure out what element it is. It'll just tell you, but you do have to look it up on the periodic table. The second symbol is called a beta particle, which is an electron. So notice that the mass is 0, if you remember that from our first chapter, and the charge is -1. Sometimes they use that beta symbol, which is this fancy B here. It's a Greek symbol. Sometimes they just use the electron symbol. This one's a little more dangerous. It can be stopped by a foil or wood, and it has a charge of -1. So we're going to do the same thing for these. Go ahead and write your beta symbol here because it's beta decay, which is an E with a 0 and -1. The top number will not change. So then you're going to put a plus and you still have 238 on the top for our last symbol, but be really careful. On the bottom, it's tempting to write a 91, but what you really need is a number where when you add -1, you get 92, and that number is 93. So you're actually going to go up 1 when you do a beta decay. So 93 plus -1 will give you 92. And if you look up 93 on the periodic table, it is Neptunium. So the symbol will be NP. So just like alpha decay, these will also change elements. And you can go ahead and try a few of these and then check with me in class and I can let you know if you're getting these right. The last type of decay is called gamma. And this isn't so much a particle, it's more of a high energy wave. And it's usually released from the nucleus in addition to alpha or beta decay. So this is the most dangerous. You can stop it with lead or concrete, but it, like I said, usually occurs in addition to one of the other ones. So I think on your worksheet, there are a couple where it has alpha decay, and then it also says gamma. So that would just be 2 types of decay in the same reaction. So go ahead and take a few minutes. You can pause the video and jot these down. This is a great summary of the particles, and this would be a great thing for you to learn for your quiz. This is just a visual so you can see how big alpha particles are compared to beta and gamma. So you notice alpha gets blocked easily, gamma is high energy and can go through most things. And our last topics for today are fission versus fusion. Those two words sound similar, but they're actually opposites. Fission means to split. So this is when you take a large nucleus and split it into several nuclei. Nuclei is the plural of nucleus. And usually we get a chain reaction from this. So those pieces then bombard another nucleus, which splits that. Those pieces hit another nucleus, and the chain reaction can continue. And in the process, we get lots of energy. The energy can be useful if we control it. So a lot of times we'll cool it down and we'll absorb some of the extra particles to slow the chain reaction down, and we can use that for power. So we can heat up water with all that energy. Water turns to steam and it spins a turbine, which then can generate electricity. And in fact, that's how most of you get a lot of your electricity, from the power plant that's located towards Apex. If it's uncontrolled, so if we just let the chain reaction go crazy, that's what an atomic bomb is, and you're probably familiar with this from history. If you remember that mushroom-shaped cloud, that was an atomic bomb. And this is how the power plants work. Notice that a neutron is bombarding a uranium atom, and then that splits, and in the process you get 3 more neutrons, which can bombard more, and that's why you get a chain reaction. And our last topic for today is fusion, which is the opposite. So fusion is putting 2 things together to form a larger one. So this is where we can take, these 2 are isotopes of hydrogen, deuterium and tritium. Most hydrogen doesn't have any neutron, but this one has 1 neutron and this one has 2 neutrons. But notice they just have 1 proton, so that's hydrogen. And when you combine them so that it has 2 protons, we get helium. And in the process, we get so much energy that you have probably been burned from this before. This only occurs on the sun or stars. We cannot get it to work very well on Earth yet because it requires extremely high temperatures to start. But if we could get it to work, this would be a fantastic energy source. It doesn't produce the radioactive waste that fission produces, and it would be a very clean energy source for us if we could figure out how to do this. But like I said, it does occur on the sun. So when you go outside and you can feel that heat on your skin, that's actually 2 hydrogen atoms combining to form helium. It's that much energy that it travels all the way through space, all those miles, and then it can actually burn your skin. If you've ever had a sunburn, it's because of fusion that you got burned. So a lot of people have trouble with these 2 words since they sound so similar. This is just a little trick to remember. If you look at the second letter, think of I for split and U for put together, and that will help you remember the difference. And that's all for today. We'll do Half-Life tomorrow.